Okay, good afternoon, everybody. It's 12 o'clock, so we'll go ahead and get started. The only reminder I have for you this week is that this week is lab number 2. Next week is our first problem session, so those things are going ahead. Before we get started for today, does anybody have any questions? Yeah.
Is that problem session open book? Do we have a formula sheet written up for it or anything?
Oh, so that's a good question. So the format of the problem sessions are, it's in your lab period, so if you're Monday's group, you go Monday morning. If you're Thursday's group, you go Thursday morning, afternoon, I can't remember, morning, I think. So you show up for the first hour. I'm gonna pass out a sheet of questions and you're gonna work on those questions. You can use all your notes, all your class resources. Hopefully you will sit with somebody else so you can work with one of your classmates. That room really lends itself to working with other people. So you might sit at a bench, there might be 2 people in front of you, you might swing around and 4 of you might work together. So you are absolutely encouraged to use all of your resources to work through it. I'll be there, the lab staff will be there, the TAs will be there, you can have as much help as you want. The goal of that first hour is to make sure you understand what we've been doing in class so far. Okay, so that's the whole point. It's why you can have all the help you want. When the first hour is up at 10 o'clock, we'll pass out a short quiz. That quiz will be based on the things you had just been doing. So if things make sense, I'll give you all the formulas on the problem sheet and on the little quiz. So if you understand what the symbols in the formula stand for, if you understand what the words mean, like what's a resonance, what's a standing wave, you should be able to get full marks on that little quiz. It's not a test level quiz, it's a check-in, right? It's sort of like the way I put up these pre-class questions. It's there to make sure you got a handle on what we've been covering so far. Okay, so did I answer all the questions asked and unasked? Okay, so that's the deal with the problem sessions. They are graded. The way I typically do the grading for the problem session, I think we have 4 of them and it's worth 10% overall. So you're gonna get 50% for showing up and doing the work in the first hour. So I think that hour of work is very valuable. That's why you're gonna get half points just for showing up and working. If you show up and you play on Facebook for the entire hour, you're not gonna get that 50%. You do actually have to do some work. And then the rest of the grade comes from the test mark. So lots of people do get full points on the problem session. Perfectly doable. Okay, so last day we were talking all about wave interference. We talked more about constructive and destructive. Got into the idea of path difference. We talked about waves which were in phase and out of phase. We looked at waves along a line and we looked at 2- and 3-dimensional waves as well. We're gonna keep going with that today. I think I've got one more example for you and then we'll be able to start chapter 19, 21, I don't know, the next chapter. So this example is the one that's going to help you with the Oscar problem on the assignment. So if you're doing the assignment and you send me an email, I don't know how to do the Oscar problem, I'm going to send you back and say, look at this example, okay? So this one is intended to help you with that. So you might notice this looks familiar from last day. I had really been hoping we'd be able to finish it, but we didn't get to it, so be it. 2 speakers separated by 12 meters. Here's you, you're standing 2.2 meters in front of one of the speakers. They're playing a tone in phase of 172 hertz, so same setup as last time. Speed of sound in air is 344. You start to walk away from the speaker as shown. How far are you when you hear loud sound for the last time? Okay, so that's what the question is. So you're walking all the way away. We know that we're talking about loud sound. So right off the bat, we know we're talking about constructive interference. The speakers are in phase, so we know what the condition for constructive interference is. It's delta D, the path difference, which is D2, take away D1, equals n times lambda, where n is an integer. We should label our speakers. I'm going to keep with what we did last time. I'm going to call this speaker 1 and this speaker 2. So notice I wrote down my delta D equation. It has an n in it. this problem doesn't say what n is. We have to figure out what n is from reading the problem and thinking about what's happening. So here's where I'm going to throw us back to what we did last day. So I'll put up this slide. We had our person standing right next to the speaker, and we found that delta D was 12 meters and n was equal to 6. So when the person was right next to the speaker, delta D was 12 meters and n was equal to 6. I'm going to put that on our diagram. So when our person was right here, n equals 6. Then in a later example, our person walked away a bit, 2.2 meters away. We saw that delta D went down to 10 meters, so our path difference decreased, and n was equal to 5. So when our person got out here, the n value got smaller, and when the person was all the way out here, this is where n was equal to 5. And these were both places of loud sound. So let's take stock and see if we can figure out what's going to happen as the person walks away. So the person is walking away. The person is going down here, 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 and here. The person is going to get to a certain point where n is going to be equal to 4. There'll be a loud sound. N equals 3 because our n is decreasing. What do you think n is going to be when we hear the loud sound for the very last time?
1.
N is going to be equal to 1. N equals 0 won't make sense. It means those two lines are exactly parallel. We can't get the parallel until we get to infinity. You can take that up with your math professors. So the last real spot we can get to is n equals 1, all the way out here. So this is going to be the last time. Here's the tricky part of this problem, is figuring out that n value. So now we're going to take this picture, put it together with this equation, and we're going to find our distance. So what we have to do in all these problems is we have to label our D1. D1 is our person to speaker 1. So from here to here, this is D1. I do not know what this distance is. I'm just going to call this distance x. This is what I'm trying to figure out. My D2 is wherever my person is now to speaker 2. To here, this is D2. Again, it's tempting to say D2 equals 12 because 12 is a number in the picture, but D2 is not 12. This is 12, this is D2. We have to use Pythagorean theorem to figure out D2. So D2 is the hypotenuse of a right angle triangle where the legs are 12 meters and x. So D2 is equal to the square root of 12 meters squared plus x squared. And D1 is equal to x. And we've established that n equals 1. So now we've got all the ingredients. Let's put it in. Let's figure out x. Any questions with the idea so far? All good? So delta D is D2 minus D1. That's going to be equal to n times lambda, but n is equal to 1 equals lambda. D2 minus D1. My D2 is bigger than D1, so I'm just going to drop my absolute value signs because I know my D2 is bigger. When I subtract them, I know that I'll get a positive value. I'll put in D2, square root of 12 meters squared plus x squared minus x equals lambda. Here's where things might get a little tangly, especially if you're a bit rusty on your high school algebra. If that applies to you, it applies to a lot of people in this institution today. Trying to learn math in high school was probably a bit of a nightmare. So let's go through the steps. I want to get at my x. So this square root is the bit I don't like. To get rid of my square root, I know I'm going to want to square it, so I'm going to get that square root on the side by itself. I'm going to take this x to the other side. Okay, this one is easier to deal with. I'm going to square both sides. So on this side, I get 12 meters squared plus x squared equals. I have to square this side. So when you square a term, I think some high schools call it FOIL method, first outer, inner, last. So x plus lambda squared, that's x squared plus lambda squared plus 2 times lambda times x. Okay. Sometimes people forget this 2 lambda x term. Just make sure you're on top of your algebra as you go through it. Something that's nice in this equation is that I've got x squared on this side, x squared on this side. So those x squareds are gone. That makes our algebra a little bit easier. So 12 meters squared equals lambda squared plus 2 times lambda times x. So 12 meters squared minus lambda squared is 2 times lambda times x. And then to get my x, I'll just divide both sides by 2 times lambda. For my lambda, you might remember this from last time, or you might calculate it again. You know, v equals f times lambda. Lambda is v divided by f. 344 meters per second divided by 172 hertz equals 2 meters. Put those numbers in the equation. What you get for your x value is 35 meters. If you're trying to anticipate, how could I shake up this question so that I asked you something similar but not exactly the same thing? I could give you that the speakers were out of phase instead of in phase. That would be a change. I could ask you to find the places where the sound is quiet instead of loud. Okay, so those are some things I could do. Okay, questions? Okay, fantastic. Then I've got another example that's a little bit similar. I've got a video made for the solution of that next homework example, so I'll post that video solution in case anybody wants to check it out. So we're going to leave this and move on to chapter 21. Any questions about any of this stuff before we leave? Okay, looks like we're in good shape. So we're going to start our chapter about electric charge and electric force and electric field. This is a really important chapter. It's kind of interesting. When you talk about the universe has 4 fundamental forces. There's the force of gravitation. We kind of all know that one. It's the weight force. It's why things fall down. There's what's called the strong force. That's the thing that holds a nucleus together. There's what's called the weak force. That's responsible for quark transformations. I do not know that much about it. And then the 4th force is the electromagnetic force. And what I think is really neat about the electromagnetic force is that all of the forces you talked about in physics 1050 or 1020, every one of those forces, except for gravity, they were all the electromagnetic force kind of in hiding. So that's kind of interesting, right? A frictional force is really an EM force, so is a tension force, so is a normal force. All of those things are truly electromagnetic. So that's kind of interesting, and we're going to stay on this topic for a good chunk of the course. So I'm going to start by telling you the list of things that I think you already know, that I think you kind of took away from, I don't know exactly when people learned these things, junior high or high school at some point. So stop me if you don't know some of these things. So materials are made up of atoms. Atoms have a nucleus. The nucleus is small, it's at the center of the atom, it's made of protons and neutrons. Outside of the atoms, we have orbiting electrons, so they go around the nucleus. Charge, this bit you might not know. For our symbol of charge, we'll always use a Q. Sometimes it'll be lowercase, sometimes it'll be uppercase. We'll go back and forth. The units of charge are called coulombs. That's after the French physicist who studied this stuff. That has a symbol of C. We're going to use most often microcoulombs. So that's a Greek letter mu in front of a C. That's 10 to the minus 6 coulombs. And we'll also use nanocoulombs a fair bit. That's 10 to the minus 9 coulombs. I do expect you to know those two, to expect what micro is and what nano is. You don't have to know the weird ones like femto and pico, but I do expect you to know micro and nano. Neutrons don't have any charge at all. Protons have a positive charge. Electrons have a negative charge. This idea of positive and negative charge, that doesn't really mean anything. You could just as well call it up and down, black and white, left and right. It just means that they're opposite. So that's what positive and negative means. So a proton charge, you might call it a Q with a little P on it. An electron, you might call it a Q with a little E on it. Something that's interesting about these charges, maybe you know this bit, maybe you don't. They have the same size of charge. So protons and neutrons, or protons and electrons, both have a charge of 1.6 times 10 to the minus 19 coulombs. The proton is the positive one, the electron is the negative one. This charge, 1.6 times 10 to the minus 19, this is special, okay? This has a symbol itself, so this value has a symbol of E, and it's called the fundamental unit of charge. So maybe you know this bit, maybe you haven't heard this bit before. What's kind of special about this is that every charge in the universe that you could possibly calculate, so you could calculate the charge on your body, you could calculate the charge flowing through the wall, you could calculate the charge in the earth, you could calculate the charge on your pencil, whatever charge you calculate, it will be an integer multiple of this charge. Okay, so that's kind of interesting. When we talk about that, we say that charge is quantized. So every charge is a multiple of this number, except for quarks, because quarks are weird. Quarks have either a third charge or 2/3 charge. We are not going to talk about quarks in this class. That's a different class if you're interested. And we also know that charge in the entire universe is conserved. Okay, so the total amount of charge in the universe is a constant finite number. It will never, ever change. We can move charge around, but we can't make up charge. So it's always going to be the same. Okay, any questions about that little blurb of stuff? I don't insist that you remember this value of the fundamental charge. Chances are good you'll probably start to remember it because we'll use this number a lot. So I would certainly give this value on a formula sheet or in a problem, but I do expect you to remember that protons are positive and electrons are negative. So you got to remember that bit. I wouldn't tell you that on a test. So you have to remember which is positive and which is negative. So let's do a quick example about this quantized charge. Yep.
Assuming it's a typo, but on your notes online it says 10 to the negative 1.
Oh, that's a stupid PDF reader. Sometimes it can't pick up that second digit in here.
Yeah.
Okay, so it printed fine
It only says it under electrons.
Yeah.
Yeah, that's the only place it says it's 10 to the negative 1, not 10
Yeah,
to the
it's definitely the minus 19. It's a printing thing going back and forth between PowerPoint and PDF. Makes me insane. Okay, I'll try and fix it, but yeah, it's definitely minus 19. So to put an equation with this bit that charge is quantized, this is not something we're going to use a whole lot. I might have one question on the assignment. We would say that total charge is the number of protons times the charge on a proton, which is plus E, plus the number of electrons times the charge on an electron, which is minus E. So this would be an equation to calculate the total charge on something. For a quick example, if we had something that had a negative 1 microcoulomb of charge, how many electrons would that correspond to? So how many electrons would we have to pile up to make that charge? So this is our total charge, minus 1 microcoulomb. So Q total is this one. We want to know how many electrons go into this, so that'll be the number of electrons times the charge on an electron. We're trying to find the number of electrons, Q total, divided by the charge on one electron. Q total is -1 times 10 to the -6 coulombs. Charge on an electron is -1.6 times 10 to the -19 coulombs. Gives us 6.25 times 10 to the 12 electrons. Okay, so lots and lots of electrons. 1 coulomb of charge is a really big charge. That's why we often deal with microcoulombs and nanocoulombs. So 1 coulomb is really big. Typically our charges will be in this family or a little smaller. Okay, questions here?
So you're dividing total charge by the individual charge of an electron?
We'll get you the number of electrons. Yeah. And what I'm doing with these couple of slides is just a quick recap of all the fundamental information from the first bits of the chapter. If you want to read a little bit more, there's sort of lots more words in the textbook, but I've got all the highlights here. So the next bit that I think you more or less know, first about the motion of charges. So in general, you can frequently think of counterexamples, but in general, protons don't move around. So wherever protons are, they more or less stay put. Electrons, some of those can move and some of them can't move. Okay, so that's the general motion. Charge flows easy through materials called conductors, and conductors would be metals. You know, copper, aluminum, and things like that. Charge doesn't flow so easily through insulators. Insulators might be like wood and plastic. And then semiconductors are something different. Depending on the nature of the semiconductor, charge flows easily or it doesn't flow easily. If you want to study semiconductors, they're really cool. That would be physics 3000. And then you'd talk about holes instead of electrons. Anyway, it's really neat stuff if you're interested in learning about those things, but that's after this. We know that there is an electromagnetic force. When we say electromagnetic force, it means there's an electric force and a magnetic force. Towards the end of the course, we'll talk about how they're kind of the same thing. So we know there's a force related to things that have charge. We know that 2 neutral objects will not attract each other. So if there's no charge at all, then there's not going to be anything happening. This is sort of neat. If you have a charged object, it can attract a neutral object. The classic example of something maybe lots of people have done, try this at home. Take a balloon, rub it on your head, really do it for a long time. If you have lots of hair, if you don't have so much hair, you can rub it on like a woolen sweater. Take the balloon, and you should be able to stick it right on the wall. Okay, the wall is neutral, but the balloon will stick. That comes through something called polarization. It just makes the wall molecules flip and line up. So the molecules of the mol are attracted to the balloon. They all line up for a short time and it ends up sticking. That's not something I'm going to ask you to define on a test or anything. It is interesting, so it's in your book if you want to read about it. Objects with like charges, so 2 positives or 2 negatives, if you bring those together, they're going to repel. You can test that out with balloons again. Rub 2 balloons on your head and try to bring them together. You'll see that they won't touch each other. They'll just get pushed apart. And if they have opposite charges, so 1 positive and 1 negative, they will get pulled together. When we measure the force between charged objects, the size of the force depends on 2 things. How much charge do we have, and how far apart are the charges? So together, these 3 things tell us about the electric force. This one tells us about the magnitude, and these 2 tell us about the sign or the direction. Okay, any questions about these things? No? Okay. So let's focus in on this electric force for a bit, and then we're going to spend an amount of time there. So Charles Coulomb was a French physicist, kind of around the late 1700s. He studied charges and electric force. He measured the electric force with a torsion balance, so he put kind of charged objects together to see what the force was. And he wrote Coulomb's law. Coulomb was by no means the only person who studied and observed electric force. Lots and lots of people did this, but he's the one who wrote the book, so he's the one who got famous for it. So Coulomb's law is an equation, and it gives us the magnitude of force between any two charged objects or charged particles. So when we write Coulomb's law, we've got to be really careful here. Notice that I said Coulomb's law gives the magnitude of the force. So this is size only, this is magnitude, this is always positive. So, and I think most people would have seen this equation in high school. I'm thinking this is familiar to people. So the size of the force is a constant times the magnitude of one charge times the magnitude of the other charge divided by their separation squared. So this is really important, is that in this equation we use magnitude of charge. So whatever your charge is, positive or negative, you put in the positive value of the charge. Okay, that's really important because Coulomb's law gives us the size of the force. So everything in this equation is positive, everything here. This R, be careful with this R, it means the distance between forces. Physicists love to use R as distance. Sometimes people get a little tangled in their head because in math, R stands for radius, which is half a diameter, and lots of people end up dividing this number by 2. I think that's just a reflex from a high school math class. So this R stands for the distance between the two charges. So physicists use R for distance all the time. This K is a constant. It's called the Coulomb constant. It has a size of 8.99 times 10 to the 9, and the units are newtons times meters squared divided by coulombs squared. This constant K, this is kind of special. It's also equal to 1 over 4 pi epsilon naught. I think this bit is probably new. I guess maybe you didn't talk about this in high school. This constant here, epsilon naught, this is a pretty special constant about the universe. It's called the permittivity of free space. It's basically a description about how an electric field can travel through a vacuum. Okay, so it's a real special constant. So that's the value of epsilon naught. K is 1 over 4 pi times that. I would give you these numbers on a formula sheet. You wouldn't have to remember these numbers. You'll probably find yourself remembering K, but probably not remembering epsilon naught. It's fine. Okay, so most often in class, I am going to be using K, but it's good to be able to recognize this. Yes?
If we were talking about electrons traveling not within a vacuum, would you just change epsilon naught to the permittivity of whatever value or whatever medium you're trying to put the electron through?
That's a really interesting question. So epsilon naught is the permittivity of free space. If charges are traveling through stuff, that's not free space. So if we had charges traveling through stuff, it would change epsilon naught, which would change K, which would change the force. We're not going to talk about those things. But yes, that is what would happen. Okay, so this gives us the size of the force. We need the direction of the force. You get the direction of the force by knowing that like charges repel, so 2 positives or 2 negatives, and unlike charges attract. We're going to do examples of this stuff on the next slide. I nabbed a couple of pictures from your textbook because I thought they were a nice addition to this slide. So, for example, we'll just look at this picture. I've got 2 positive charges. They're called Q1 and Q2. They're positive, so they're going to repel each other. So if I asked what is the force because of charge 2 on charge 1, I would know it gets pushed away, so my force is away. If I was going to write down the size of that force, I would say that it was K times Q1 times Q2. The distance between them is labeled in the picture as R, so I would do that divided by R squared. Then to make it a vector, I would include the direction, and I would say away. And then, let's just look at this for a moment. If, on the other hand, I asked what is the force on charge 2 because of charge 1, well, I know it's repelled, so it gets pushed away. So there's my direction on the picture. If I wanted to find the magnitude, it would be K times Q1 times Q2 divided by R squared. Direction is away. What do you notice about the magnitudes of those two forces? They're exactly the same, right? They both have K, they both have R squared, and they both have same charges. This makes sense when we go back to Newton's third law. Okay, for every force, there's an equal and opposite force. If I push on you, then you push on me with the same force, just in the opposite direction. So the forces on 1 and the force on 2 is a Newton's third law action-reaction pair. Okay, so we never get to leave Newton's laws behind altogether. Okay, so there's our summary. Now we'll move on to examples. Anybody have questions about the ideas before we move on? Okay, so let's get started with our examples. So in our example, I've got a picture of a helium atom. In this helium atom, I've got my nucleus. My nucleus has 2 protons and 2 neutrons. So here in the center is my nucleus. It's got 2 electrons orbiting around on the outside. I know that my nucleus has a size, or a diameter, of 3.36 times 10 to the minus 15 meters. So that's how far apart my protons are. And my electrons orbit at a distance of 0.208 times 10 to the minus 9 meters from the nucleus. As a reminder, I put the charges here just so we didn't have to write those out again. Parts A and B, find the force between the protons and the nucleus. Part B, find the force on one of the electrons by the nucleus. And then part C is to think about that action-reaction pair and find the force on the nucleus by the electron. Okay, so that'll be the homework question. So let's get started with part A. So I'm just going to do a quick sketch. So here's my nucleus. I've got 1 proton here. I'm going to call that charge 1. I've got a second proton here. I'm going to call that charge 2. I'm going to put a plus sign next to each of those just to remind myself that the proton is positive. Okay, I think that's a little better. The 2 protons are separated by distance. We always call that distance R. So let's write down the things that we know. The size of the charge 1 is the fundamental charge E. The size of charge 2 is the fundamental charge E. That distance R is the size of my nucleus, 3.36 times 10 to the minus 15 meters. So I want to find my force. Right off the bat, before I start doing any math, I'm going to draw the direction of the force. They're 2 positive charges. They're going to repel each other, so the force is going to be away on each of them. So proton 2 is repelled by proton 1. Proton 1 is repelled by proton 2. Okay, so there's the direction of the force. So repulsive or away, whichever way you choose to write it down. Do the magnitude of the force next. So the magnitude of the force is given by Coulomb's law. K times the size of charge 1 times the size of charge 2 divided by the distance between them squared. Charge 1 and charge 2 have the same magnitude, so size of Q1 times size of Q2 is going to be E times E, or E squared, equals 8.99 times 10 to the 9 newtons meters squared over Coulomb squared times 1.60 times 10 to the minus 19 coulombs squared divided by the separation 3.36 times 10 to the minus 15 meters. That force, when you do it in the calculator, is 20.4 newtons, and then I'm just gonna write in the word repulsive, because I know they repel each other. I would like for you to think about this force for a moment. A proton has a mass of 1.67 times 10 to the minus 27 kilograms. If we apply a force of 20 newtons to something with a mass of 10 to the minus 27 kilograms, what happens to it?
It breaks apart.
It would break apart, right? So F equals ma, A is F over m. We have this big force divided by this teeny tiny mass. One would anticipate that those two are going to fly apart as fast as possible. This is where we circle back around to the strong force. So one of our fundamental forces in the universe is a force between these two that actually holds the nucleus together. I think that's really cool. Okay, so there's a force bigger than this one that makes those protons not split apart. Okay. No, that's not going to be on the test or anything, but it is pretty darn cool, I think, anyway. Okay. Any questions about this? No. Okay, so next question. Find the force on one of the electrons by the nucleus. Doesn't matter which one we pick. So for part B, I'm going to draw a second picture. So I'm going to draw my nucleus. In my nucleus, I have two protons. So I'll put two plus signs in there. I'm going to call this charge 1. I have an electron outside, so that's a negative sign. It's orbiting around the nucleus. So I'll just put a little arrow to show the direction of the velocity, just because that's kind of interesting. I'm going to call this Q2, my second charge. Like I did up here, I'm going to put the direction of the force on that. So the force is attractive. This electron is attracted to the nucleus. So there's the direction of the electric force. So let's use Coulomb's law to find the magnitude of the force. So the force has a magnitude of K times the magnitude of charge Q1 times the magnitude of charge Q2 divided by R squared. R is the distance between the nucleus and the electron. So I've got K. The magnitude of charge Q1 is the charge on the nucleus. There are two protons in the nucleus, so the total charge would be the proton plus the proton, so 2 times the charge of a proton, or twice the fundamental charge. The magnitude of the charge on an electron is just the fundamental charge, divided by R squared. So I've got K times 2 times E squared divided by R squared. Good to hear, it's just a little bit of algebra so far. Okay, put the numbers in next. 8.99 times 10 to the 9 newtons meters squared over Coulomb squared times 2 times 1.6 times 10 to the minus 19 coulombs squared. The distance between the nucleus and the electron is 0.208 times 10 to the minus 9 meters. Don't forget to square that. So we get the force on the electron is 1.06 times 10 to the minus 8 newtons. And then to put in the vector bit, we'll say it's attractive.
So does that mean that it's accelerating like incredibly fast?
Yeah, the acceleration is huge.
Yeah.
Yeah, because the mass of the electron is even tinier, right? That's 10 to the minus 31 kilograms.
Like where force is 20 newtons divided by that ridiculous small number.
Yeah.
So acceleration feels like times 10 to the 30 years.
Yeah, huge, right? Yeah. So the top one, the acceleration is actually 0 because of the strong force. There's another force in this picture that we're not talking about.
Right.
So this is just the electric force.
But the electron one is.
Right, and then this one is really interesting. If we wanted to think about this one for a moment, the force is towards the center, but the velocity is going around in a circular orbit. This is actually a centripetal force. Okay, so the force is towards the center, it's perpendicular to the motion. There's lots of stuff you could do right here. We know that F equals ma, that's definitely true. But when things go around in a circle, you could say A is V squared over R. you could use that bit of information to figure out how fast the electron is going. Okay, so that's kind of interesting too.
Doctor, you forgot to spell the number in the first one.
Oh, didn't write down this yet. Yeah. Okay, any questions? No, okay. So that was our starter problem. Between two charges where things are more or less in a line. Let's get into one where problems are a little bit more vectory. Yep.
With regards just to the homework question, I know that you're not gonna answer the full thing, but, is it based off of, like, where the attraction force is going? Is it based always off of the density of the nucleus, or is it based off of the charge of each? Like, if one's more dense, is that what's going to be, the attractive force is going to be towards, or they both have the same attractive force?
They both have the same attractive force, just like the Earth and the Moon. They pull on each other with the same gravitational force. Yeah. So we should get exactly the same answer.
Okay.
Yeah. Okay. And I will post the solution for that. I think I haven't written it up yet, but I will write it and post it with the notes. Yeah. Okay, so next problem. So a typical problem you're going to see is a set of charges, 3 or 4 charges, find the force on one of the charges. So this is a pretty typical kind of problem. So in this picture, I've got 3 charges. I've got them in an equilateral triangle. That's what these sides are showing. My charge at the top has got a little q. It's 0.5 microcoulombs. My charges on the bottom of the triangle are plus and minus charges, and those have a size of 1 microcoulomb. So these are bigger than this charge. My equilateral triangle has a side length of 1 millimeter, and we'd like to find the net force on the charge at the top. So we want the force on this charge. The process, I sort of typed out the steps here just so it looks kind of nice. This is very much like a Physics 1020 or a Physics 1050 problem. So in Physics 1050 or Physics 1020, you had a few forces. You had to find the vector sum. So you had to find the components, add the x's, add the y's, write your answer as a vector. We got to do the same deal here. There's only one additional step, is that in Physics 1050 or 1020, you were usually given the magnitudes of all the forces, and you had to do the addition there. We have to do the intermediate step of using Coulomb's law to find the magnitude of the force. Once we do that, then we can do our vector addition. So our first step in this process, just like 1050 or 1020, we need to draw a free body diagram. So we have to draw the forces on the charge. So I'm going to give you all a minute, and I want you to draw those forces. This is a really important step. Everybody should do this, because usually a third to a half of the class will not get this diagram right, and they'll end up kind of only getting half marks on a test problem. So I want to make sure that you can identify for yourself that you can draw these diagrams. So you give it a shot, and then we'll do it up here.
Should we draw our diagrams based off center point mass, or should we do it?
You can assume they're point charges. Yeah. Okay, I think that was probably enough time for everybody to sketch out their answers. So while you were drawing yours, I've gone ahead and I've labeled the charges 1, 2, and 3. That's just to make it easier for me to label my forces. So the top is charge 1, the lower left is charge 2, and the lower right is Q3. So if I want to find the force on charge Q1, think about in Physics 1050 or 1020. If you wanted to find the force on a box, you drew your forces on the box. Same thing here. When you draw your forces, you have to draw them on this charge. So your pen has got to go on top of charge Q1, and then you have to draw your force in the appropriate direction. So we'll do the force due to Q2 first. So my Q1 is here. These are two like charges. Q1 is going to get pushed away from Q2. So there is my force on charge 1 because of charge 2. I'm going to label that F2. Sometimes people will put that charge down here on this one. We'll push that this one goes away, or they'll put it right here going into here. This is where that force has to be drawn. So your picture has to look like this. Okay, likewise with charge 3, this is positive, this is negative. What happens to charge Q1? It gets pulled towards Q3. It's an attractive force. So I'm going to draw an attractive force, and I'm going to label it F3. If you drew your force down here on Q3 being pulled out, or if you drew it out here being pushed down, those would not be considered correct. Okay, so this is what your diagram needs to look like. Super. So that's step 1 of the process. Draw the free body diagram, draw the forces on the charge that you're trying to calculate the next force on. The next bit, we're going to use Coulomb's law to find the force. Yep.
Would you include force of gravity on the proton?
Oh, that's such a good question. I'm really glad you asked. Force of gravity definitely exists. It's definitely true. The force of gravity tends to be really small for all these problems, like 10 to the minus 40 newtons. So for most problems, we're going to neglect the force due to gravity. The only times we wouldn't neglect it is, I would say, in this problem, a heavy charge, a charge of mass 10 grams. Those are clues you have to include weight, but typically we're going to neglect it. Great question. Yep.
I was going to say because of the mass of the protons are really small, so
Yeah, absolutely.
Are we assuming this is at equilibrium, or is this like an instantaneous, are we looking at the instantaneous force on the?
Yeah, when they're all in this place.
Okay.
Yep. So we want to use Coulomb's law to find the magnitude of each force. So let's do F2 first. So the magnitude of F2 equals K times the magnitude of charge 1 times the magnitude of charge 2 divided by the distance between them squared. So this is the distance between 1 and 2. In terms of the numbers we have in this problem, we've got K times the lowercase q times the uppercase Q divided by d squared. For the sake of getting these magnitudes done before we have to quit, I'm not going to write in my numbers. That turns out to be 4,495 newtons. For my force F3, that's going to be K times the magnitude of charge 1 times the magnitude of charge 3 divided by the distance between 1 and 3 squared. So that's going to be K times lowercase q. Remember, these are magnitudes of charges. The magnitude of this charge is plus q divided by d squared, also 4,495 newtons. Our next step is going to be to find the components and then to take the vector sum. But we'll quit right here for today, and we'll finish this on Wednesday. If you want to get a head start, you certainly can give it a shot, but we will finish it in class. Today is my day I run to my next lecture, so I don't have